So we want to look at the following. Let's suppose we have some function here, and it looks something like this. And we are interested in finding the slope of a line tangent to the curve at this point right here. And let's say furthermore that that's the point 2, 4. And I want to find the slope of a line that touches this curve just at one point, so the slope of the tangent line. How can we go about doing that? Well, we could pick another point up here on the function, call it x comma g of x. Say our function is g. And I could look at the slope of, this is called the secant line. It's a line connecting 2 points, the function. I could look at the slope of that secant line, and it would be an estimate for the slope of the tangent line. What's going to make that estimate better and better is if this point, as it comes closer and closer to 2, 4, that secant line is going to come closer and closer to matching up with this tangent line. So, how can we set that up as an expression? Well, we could say, let's let the limit as x approaches 2 of the slope of the secant line, which is going to be y2 minus y1 over x2 minus x1. So that would be g of x minus 4 over x minus 2. If I look at the limit as x goes to 2, it looks like that's going to give me the slope of the tangent line. And that's great, except for the fact that if we go ahead and try and just plug a 2 in, g of 2 is 4, 4 minus 4 is 0, 2 minus 2 is 0, and we get that very nasty 0 over 0 indeterminate form for a limit, and we would have to manipulate the expression to figure out what that limit could be. So let's suppose we have a specific function. Let's let our function be g of x. Again, I'm looking at the limit as x heads to 2 of g of x minus 4 over x minus 2. That would be the slope of my tangent line here, y2 minus 1 over x2 minus x1, and I want let that x value come closer and closer to 2. And if I now go ahead and plug in what g of x equals, this would be the limit as x approaches 2. If g of x is x squared, that's going to be x squared minus 4 over x minus 2. If I go ahead and just plug in a 2, I get 0 over 0. That's a problem. But now we're back to a limit problem that we've looked at for the last couple days. The limit as x approaches 2. I can factor that top expression, x plus 2, x minus 2 over x minus 2. X minus 2's will cancel, and as x approaches 2, my limit will be 4. So again, let's think about that. What did we just show? We just showed that for the parabola, x squared, the slope of the line tangent to the curve at 2, 4, the slope of that line is 4. So if we go ahead and generalize this, we say, well, instead of some specific point 2, 4, let's suppose we have a point x g of x, and we want to find the slope of the line tangent here, x g of x. If I go over here h units to the right and find another point in the graph, x plus h, g of x plus h, the slope of that secant line will be an estimate for the slope of the tangent line. The closer that the point x plus h gets to x, viewing that as a limit, it's as h heads to 0, as h gets smaller and smaller, x plus h will approach x, and g of x plus h will approach g of x. Indeed, that's going to pull, as h goes to 0, it's going to pull this point right toward x g of x. So I want to look at the limit as h heads to 0 of g of x plus h minus g of x all over x plus h minus x. And you can see that when you simplify that, you get the limit as h goes to 0 of g of x plus h minus g of x all over, well, x plus h minus x is just h. And again, if I look at that, I see that I've got that 0 over 0 ambiguous, what's called indeterminate form cropping up, because if I just plug an h as 0 in, I've got g of x minus g of x is 0 in the numerator. If I plug h in the denominator, I get 0 over 0. And clearly I'm going to have to do some manipulation to allow me to compute the limit for specific functions. But there is what we have. We have an expression for the slope of the line tangent to the curve for this given function. And we're going to say that expression is the derivative of the function. We say that this expression right here is the derivative for the function g of x. In other words, the expression that gives us the slope of the line tangent to the curve of a function at a given point on the function is called the derivative of the function. And note, the derivative of the function will also be a function, as we will see here shortly. So let's look at this derivative function, this limit that gives us a function, and let's look at the specific function x squared. For x squared, we'd be looking at the limit as h goes to 0 of g of x plus h if g of x is x squared, it's going to be x plus h quantity squared minus x squared. X plus h minus x is simply going to be h. And again, if I let h be 0 here, just plug in h as 0, I get x plus h quantity squared is h. If I plug in h as 0, I get x squared minus x squared at 0 over 0, nebulous, indeterminate form, no good. But I look at this and I see that I've got a quadratic, and when I expand this, I'm going to see an x squared and a negative x squared. Those are going to cancel. So go ahead and do some algebra, manipulate this expression that gives me that 0 over 0 bad news form. And let's see what happens when we expand. Well, we then get the limit as h approaches 0 of the x squareds will cancel. That would be, plus. It would be 2xh plus h squared all over h equals the limit as h goes to 0. Well, an h will cancel out of everything, so that gives me a 2x plus h. What's the limit now as h goes to 0? Where is that thing? Get back here. What is my limit as h goes to 0 of 2x plus h? And that clearly is h goes to 0 is just 2x. So note, we started with a function x squared. What does that function look like? It's a parabola. There it is. We've come up with a rule that gives us the slope of the line tangent to the curve at any point on the curve. And the rule is the slope of the line will be x squared. X squared is a function, the slope of the line will be 2x. Note that 2x is a function as well. Does that make sense? Does it fit in reasonably with what my parabola does? As x increases, are my slopes of the tangent lines going to increase? Yes. So as x increases, 2x gets bigger and bigger. Check, that looks good. How about right here at x equals 0? At x equals 0, I got a horizontal tangent whose slope is 0. When I plug 0 into this function rule, 2 times 0 is 0, yep, that looks good. And how about my slopes over here? They start off negative and they get steeper and steeper. As x decreases from 0 down, these values get smaller and smaller, and indeed, I also see that if I put in, for example, x equals 2, I'm going to get a slope of 4. If I put in x is negative 2, I'm going to get a slope of negative 4. And that symmetry about the y-axis here is expressed, is consistent with what we got for 2x. So suppose you're asked to find this derivative for g of x equals the function 4x cubed minus 2x squared. We saw the limit as h goes to 0 of g of x plus h minus g of x all over h. That's our limit for the secant line approaching the tangent line. So now I go ahead and just g of x is 4x cubed minus 2x squared, so I'm simply going to plug in. It's not going to be fun algebraically perhaps, but I'm simply going to plug in x plus h for x, so I'll get 4 x plus h quantity cubed minus 2 x plus h quantity squared. That's g of x plus h minus g of x is 4x cubed minus 2x squared all over h. And I look at that, if h goes to 0, as h goes to 0, I get 4x cubed minus 2x squared minus 4x cubed minus 2x squared, I get 0. And in the denominator, I get 0. I get that 0 over 0, which means I can't, as of right now, evaluate this expression. And so we want to expand, manipulate algebraically, and see what we can come up with. So I need to take that limit as h goes to 0. I need to expand in here. I've got a cubic expression, so 4. And when you expand by FOIL, you get x cubed plus 3 x squared h plus 3 x h squared plus h cubed minus, I'm going to have to make this smaller here, minus, let's see, 2 times x squared plus 2xh plus h squared. That's going to be this expression here expanded. Minus quantity 4x cubed minus 2x squared all over h. Go ahead and multiply out. We get the limit as h goes to 0. And I get 4x cubed plus 12x squared h plus 12x h squared plus 4h cubed minus 2x squared minus 4xh minus 2h squared. And then taking that negative through, minus 4x cubed plus 2x squared all over h. Well, 4x cubed and negative 4x cubed gone. I got a 2x squared and a negative 2x squared gone. And then that leaves me the limit as h goes to 0 of 12x squared h plus 12x h squared plus 4h cubed minus 4xh minus 2h squared all over h. I can factor an h out of everything in the numerator, and that will then cancel the h in the denominator. So I get the limit as h goes to 0 of 12x squared h plus, 12x squared, if we factor that h out of there, 12x squared plus 12x h plus 4h squared. Then I have minus 4x minus 2h all over 1. So what's the limit as h goes to 0? Well, I get 12x squared minus 4x. So that we got to be the derivative expression for, remember, our original function was g of x was 4x cubed minus x squared. And I want you to look at that for a minute. 4x cubed and 12x squared. The exponent dropped by 1 in each case. We went from 2 to 1. We went from 3 to 2. And what happened out front here? How do we see any relationship between, well, that was minus, the function was minus 2x squared. Do we see any relationship here between exponent and coefficient that would, these numbers appear down here? And you should see that 2 times 2 is 4, and 3 times 4 is 12. And that will then lead us to a general rule, which we'll look at a little bit more in class, for the derivative of any monomial or polynomial function. So, again, our general rule, which you're going to prove in calculus next year, if I have a monomial function, say ax to the n, then the derivative will be given by take your power, multiply by the coefficient na, and decrease your power by 1. So, for example, if I have h of x is 12x to the 4th, my derivative would be 4 times 12 is 48, drop the power by 1, x cubed. A couple other things to notice. When we took the derivative of found the derivative for g of x being 4x cubed minus 2x squared, note each of these is a monomial, so I have a polynomial. The derivative by our definition turned out to be 12x squared minus 4x. That would be the derivative of 4x cubed, 12x squared, minus 2 times 2 is 4x to the first. So it looks like if I have a function that's a combination of two other functions added or subtracted, the derivative turns out to be the derivative of each of the terms in that addition or subtraction of functions. We can generalize that and say, if I want to find the derivative of some function f of x plus g of x, the derivative of that is going to be given by the derivative of f plus the derivative of g. And this notation is called derivative notation. We would read it as prime. We would say g prime of x equals 12x squared minus 4x, f prime of x plus g prime of x. And we just are going to use that called derivative notation, prime notation for our derivatives. And in this case, again, g of x is 4x cubed minus 2x squared. G prime of x is 12x squared minus 4x. Last thing to consider, suppose you have some function that's linear. Say f of x equals 2x plus 1. Y-intercept of 1, slope of 2. Now, considering derivatives, we said the derivative is the slope of the line tangent to the curve. Well, this isn't a curve, this is a line, and we've said we're really considering that slope to be a rate of change. Lines have a constant rate of change. Slope is constant. That's what makes it linear and makes it a line. Our slope is 2. So if I've asked you to find the derivative of a linear function, it's simply going to be the slope of the line, except in the case if a line is vertical. If I have a vertical line, like so, x is 4, what would we say the rate of change is? Well, we would say that the slope of the line is undefined, and there will be no derivative. A vertical line will have no derivative. Furthermore, a vertical line, you'll notice, isn't a function because for any input we get multiple output values. So for many reasons, the vertical line is, we say the rate of change is undefined. So at any rate, going back here to our linear case though, fx equals 2x plus 1, we say if I ask you for the derivative, it'll simply be that constant rate of change, which is the slope, which is 2. Is that consistent with our rule that we just looked at, where the derivative is the product of the coefficient and the exponent, and then you drop the exponent by 1? And sure it is, because our exponent here for a linear case is 1. 2 times 1 times x to the 1 minus 1 is 2 times x to the 0. X to the 0 is 2. So my rule is still consistent with this. I get a slope of 2.